Have you ever wondered what really is there in space? Get ready to go on a journey to explore two of the most strange objects in the universe, black holes and neutron stars. Neutron stars were discovered in 1967 when Jocelyn Bell Burnell spotted a weak repeating signal using a large radio telescope. Black holes were found in 1916 when Carl Schwarzschild solved Einstein's equations. Now you're going to learn what they are, how they're made, why they're made into different forms, how the threats to the universe compare, and how the study of black holes and neutron stars expanded over time. But let's start with what exactly are they? Neutron stars and black holes are both remains of stars that are extremely dense and have huge amounts of gravity. Science.nasa.gov says, when a star bigger and more massive than our Sun runs out of fuel at the end of its life, the core collapses while the outer layers are blown off in a supernova explosion. If the star was 7 to 19 solar masses, it becomes a neutron star. If more solar masses, it becomes a black hole, less and it becomes a white dwarf. Do you know that one solar mass is the mass of our Sun? Neutron stars are formed when a massive star runs out of fuel and the core collapses, pushing every proton and electron into a neutron. Gravity is extremely strong on a neutron star. A neutron star weighs 100 million tons, and the magnetic fields of a neutron star can release gamma rays. The temperature is about 1.8 million degrees Celsius, and they can rearrange all of the matter in our bodies. A neutron star is between 1.18 and 2 solar masses. There are many types of neutron stars, including magnetars, pulsars, X-ray pulsars, and binary neutron stars. These are only some of the countless neutron stars, and there might be another one found right now. The important ones are pulsars and magnetars. Pulsars are the neutron stars that have their high energy beams pointed at Earth. They also spin the fastest of any type of neutron star. But magnetars aren't like pulsars. They're the dangerous part of neutron stars. What really makes a magnetar so powerful is the magnetic field. The magnetar can melt you as well as all its neutron star capabilities. That is what the mysterious neutron stars are. Black holes are not actually solid and are invisible because light cannot escape it, and you can only detect them by using radio waves. Black holes suck everything in and nothing comes out. The point of no return is known as the event horizon. In this, you would be stretched thousands of miles long, and this is called spaghettification. Black holes also usually have planets or objects orbiting it. Outside of black holes, it is billions of degrees, but on the inside, it's close to absolute zero. Languages OUP says, the lowest temperature that's theoretically possible at which the motion of particles that constitutes heat would be minimal. Absolute zero is minus 273.15 Celsius, or minus 459.67 Fahrenheit. The singularity is a spot where there's infinite gravity, where mass is compressed in an infinitely small point. There are three types of black holes: supermassive, stellar mass, and intermediate mass. Supermassive black holes are weak, but if you fell in it, you would still get stretched and the singularity would kill you. Intermediate mass black holes are just smaller, but the smaller the black holes, the more powerful. The reason for this is a black hole and neutron stars are stars being compressed into small objects. Stellar mass black holes are the most dangerous, though. They are the smallest black holes. These black holes are the ones that have the planets and other objects orbiting it. They are 1,560 light years away, so there's nothing to worry about. Black holes have a right to be feared, though. The first black holes were formed in the early universe right after the Big Bang. Black holes form when the center of a very massive star collapses in upon itself, causing a supernova. When a star is a bit less massive than the star, they explode and leave behind neutron stars. There are also things stars could become if they're neither. Once scientists found something too big to be a neutron star, but too small to be a black hole orbiting a star. It was 2.6 solar masses, and that is above the limit for neutron stars, so why can't it be a black hole? You've never noticed a black hole under 5 solar masses. This star could be neither or both. If it was both, the result could create a catastrophe. Thankfully, this has not happened. Stars cannot be too big to be a black hole or too small to be a white dwarf. A black hole is made from a star collapsing, so it cannot overcollapse. It will just be a larger black hole. White dwarfs are made when a star cools down, so it will just cool down into a smaller white dwarf. That is how black holes and neutron stars are made, and why they're made into different forms when they're both from stars. Neutron stars and black holes are both threats to the universe. Neutron stars have enormous gravity, spin fast, and unleash gamma rays. Cause starquakes, rearrange all the matter in our bodies, and magnetars can also melt you. Those can fry you and freeze you, and they can also smash you to bits. Finally, they can stretch you thousands of miles long. Black holes have more gravity because the original star that the black hole formed from has more mass than the one neutron stars came from, and black holes and neutron stars are something with a lot of mass squeezed into a tiny space. We study black holes with machines that can detect different wavelengths. Black holes can be surrounded by rings of gas and dust, called acceleration disks, that emit light. Since black holes don't emit light or reflect it, they appear invisible. But neutron stars are usually observed to pulse radio waves and other electromagnetic radiation. To tell almost everything about a black hole or a neutron star, you need to detect the ripples in space-time created when the two of them crash into each other. But that might be a problem. Think of this: if a black hole emits some wavelength and it goes to another black hole, we only get part of the black hole data or none at all. This isn't a problem for pulsars because we can only see pulsars if we detect them at the right. One advance is when a research team introduced a new model of molecular clouds. They found that the growth of black holes primarily occurs through the acceleration of molecular clouds during galaxy mergers. But there's not much neutron star study change since neutron stars are relatively new, but they're being studied a lot. The study of neutron stars and black holes has expanded over time by machines and knowledge. We're trying to learn more every day. Ultimately, neutron stars are more of a threat because they have huge amounts of gravity, spin very fast, emit gamma rays, rearrange all the matter in our bodies, and magnetars can melt you. Black holes can fry you and freeze you, smash you to bits, and spaghettify you. These are all powerful skills, but in the end, neutron stars are more destructive, and scientists are trying to build better telescopes and discover new ones. What do you think about this?